Okay, so I think we can start. So welcome everybody in this week Quantum Technologies and Quantum Information seminar. Yeah, it's a great pleasure to have Zoltan Zimboras with us. So Zoltan is actually my long-time collaborator. So let me introduce him to you. So Zoltan, after doing PhD in Zoltan specializes in various fields in quantum information, quantum computing, let's say ranging from man-in-body physics, like mathematical quantum computing, up to like those recent developments surrounding near-term quantum computers. Zoltan did his PhD in Wigner Institute in Budapest. Then you had 4 postdocs. That's impressive number in in Torino, Bilbao, UCL in London, Freie University, Berlin, and now he's group leader of quantum computing group in Wigner, and affiliated with a company, quantum software company, Algorithmiq, based in Finland. But he's also moving for a new permanent position to Helsinki University in Finland. Right, and today he'll be telling us about like some recent developments, regarding power and limitations of near-term quantum computers. Please, Zoltan, it's great to have you.
Thank you very much, Michał. I hope you hear me well. So exactly as Michał introduced my talk, I'm going to talk about both the power and the limitations of near-term quantum computers. And this is like a very hot debate. People have different type of views, and a lot of politics, economics, and even emotions fly around this topic. So actually, I'm going to be also subjective in some sense, but I think what I'm going to tell you is a point of view which many people share, and the reason also what I'm going to tell you is because some of the recent results around the limitations of near-term quantum computing, which I will talk a little bit what I mean by that, is interpreted in a little bit wrong way, so as you will see. So that's the title, like that there are these myths around quantum computation before full tolerance. This is what we'll talk about. So basically these Nisky type of machines, and what the no-go theorem rules out and what they don't. And of course, there is this term called NISQ, which is the noisy intermediate scale quantum computation. I mean, this term was coined in 2021. But of course, the main results about like how to deal with noisy computers before error correction, which I will talk a little bit about, was before that. But actually, it was John Preskill who coined this term, and then it made it into a field. And there is this, let's say, infamous or famous conference called Q2B. And in 2021, this is a picture of Preskill talking there, and also about his newly coined term, NISQ, and he said that physicists are excited about this NISQ technology, which gives us new tools for exploring the physics of many entangled particles. Just 2 years later, in the same conference, Q2B, he said something completely different. He said that what we can reasonably foresee, that nor are there persuasive theoretical arguments indicating that commercially valuable applications will be found that do not use quantum error correcting codes and fault-tolerant quantum computing. And then he was saying that probably we should focus more on the fault-tolerant stuff. So after this, of course, there were many memes. I will only show you one meme of this, which is this, like, Preskill it was not 21, but in 2017 when he coined it, and 6 years later. So what my talk is going to be is that I acknowledge 2 things. First of all, there were really, really many bad NISQ proposals in the field. And this is because of this field, this NISQ field, got a bad type of taste for many. Secondly, there is what we in the end want to do is fault-tolerant quantum computation with quantum error correction. These are the two things I'm going to acknowledge in the beginning already. And also I'm acknowledging that there are huge amount of experimental progress in quantum error correction that is towards fault-tolerant quantum computation. But I would argue that it's very, very far away. And the rest of my talk is going to be about arguments why I still believe that we have overlooked in NISQ some very important aspects, and I'm going to go through these myths how people, from a theoretical point of view, argue against NISQ. And I think this is sometimes not a good argument, and then talk a little bit about these things. So before I'm going to go to the myth, I have to tell you, maybe to those who are not that much into quantum computation, about how to handle errors and noise. So there are three words that you will often meet. One is error suppression, the second is error mitigation, and the third one is error correction. Oh, sorry, my slide went back. So error suppression is it's just clever physics. It's a basic error handling technique that uses knowledge of the undesirable effect inside the quantum devices and operate close to this. So you can think of, for example, dynamical decoupling, or dynamic decoupling is a method of like that where you can remove some type of noise in the hardware level, immediately remove in the hardware level. Error mitigation, on the other hand, is a way to reduce and eliminate noise effects, typically noise effects of within expectation values when we run a quantum circuit. Just by running different type of quantum circuits, noisy quantum circuits, maybe not only the quantum circuit that you really want to run, like a noisy version of that, but also other quantum circuits, and then analyze the outputs and post-process the outputs in a way such that you will get out the noiseless expectation value. So I mentioned here two error mitigation methods. There are many more. The probabilistic error cancellation. What this does is that it models a hypothetical scenario where you remove the noise in a quantum circuit. So you can imagine that you want to run the U1, U2, UL circuit, what you have here, but of course there is a noise channel, lambda 1, lambda 2, lambda L, acting on that. And then what you could do is to apply an unphysical map, and I will tell you how you can apply that. A lambda 1 minus inverse, lambda 2 minus inverse, lambda L minus inverse. And the application is done only on paper first. So you apply, like, if you would apply, how would it affect that circuit? And what would happen is that you get new circuits. You get your linear combination, not with positive coefficients, of expectation values of some observables that you measure at the end, but run over different type of circuits. And of course, what the price to pay is that you have to run different type of circuits to get expectation value of one particular noiseless circuit. And you have to do a lot of samples. You have to do a lot of runs to make it precise. And there is a precise mathematical theory of this. Another one, which is there are no guarantees, is this zero noise extrapolation. What you do there is that you run a noisy circuit, and then you, in a systematic way, add more noise. And then, also in a partially systematic way, connect the expectation values of the different noise levels, and then extrapolate to the noiseless value. This is the zero noise extrapolation. And the final one, which, sorry for this happened. I don't know how this happened. I didn't maybe check the PDFs carefully. So the final one is error correction, where you encode the quantum information of a logical qubit into many physical qubits, the qubits in the devices which are noisy. And actually, if you have just a couple of couple of errors occurring among the physical qubits, you can recover with active error correction the original state. And of course, based on this, you can build up fault-tolerant quantum computation. And there is this important threshold theorem, which says that if the noise is beyond some break-even point, then you can encode the quantum information of one qubit into bigger and bigger number of physical qubits. And then actually that logical qubit will be have less and less errors. Actually, it will exponentially decrease the error in that case. Okay, so since we have discussed these different type of error handling methods or noise handling methods, let's talk about the myth which are giving you negative arguments against the second one. The second one, this is this regime that we are working in now, where there are many experiments on error mitigation, but people often say that it will never get you any useful information. And the first myth around this is that quantum error mitigation cannot be useful due to the scalability limitations revealed by recent no-go theorems. Okay? So basically, these recent no-go theorems are based on the following observation. If you have certain types of noise, which are called unital noise, then if you run the quantum circuit from any state, basically, then it becomes more and more close to the identity state, so the completely mixed state, so the white noise. And from white noise, you cannot get any interesting information. So only to distinguish your resulting state from the completely mixed state white noise, you would need to have exponentially many measurements. So they give you a lower bound on the error mitigation methods. Okay, exponential in what? This is what I'm going to discuss. Okay? And exponential in what? I will tell you about the theorems, but I will show you that this was nothing new to the people working in NISQ, of course, because, for example, in this probabilistic error cancellation model, where you had an n-qubit circuit with depth L, and what you were doing is that you could obtain, you can run n-qubit circuits with depth L and noisy circuits, but you want to obtain the expectation value of the noiseless circuit. And what you do, as I told you, by some mathematical trick, it means the same thing as running different type of n-qubit circuits with depth L, and in some way adding those expectation values. And actually, they actually even calculated what the sample overhead for this means, that you have to take much more samples, much more measurements. And what you would have to do was that you had to do, if you had the 2-qubit rate error epsilon with n qubits and del epsilon, there was an exponential sampling overhead 2 to the epsilon n times L. Okay? And here I just show a theorem about this in this Nature Physics paper from 23. And there was, of course, the original paper from 17. And then there are also other methods. I told about the Z and E, which has a much less, much less, meaning that in the exponent you have just epsilon n times L. And also there is the TEM, the tensor network error mitigation method, which this company that I work in, Algorithmiq, introduced. And then there is also the a very nice method, purification-based method, which don't actually need error characterization by the other three means. They have that has a similar sample overhead, 2 times epsilon and L. So these were known already, these overheads in 2017. Just to tell you, and people did a lot of experiments. And suddenly, okay, there were these number of papers, 2022, 2023, 2024, in very nice theoretical paper appearing in big journals, Nature, Physics, PRL, and so on. But in the end, the only thing they were giving, or which is a lot of things, is that they gave rigorous lower bounds. And the rigorous lower bounds matched the upper bounds that these actual error mitigation papers give. So it's exponential of the sampling overhead will be exponential of epsilon, the 2-qubit error, times n, the number of qubits, times L, the depth. This is what they proved. All of these, very nice theoretical work, did not, and now I'm going to emphasize, there was a lot of hassle, especially from the Nature Physics 2024. Now error mitigation is over, everything is gone, nothing. They did not give any new thing about the scaling. They just expanded the type of noise models, and when this is true, this formula, but the formula is the same as the 2017 NISQ formula. So when you read the paper, that now this paper shows theoretically that it did not work, it's like, no, the paper just says that there cannot be any other method, but this method, we had the same exponent for this method. So this is my first argument. Second, there was also another paper, I'm sorry that I'm gonna criticize that paper, which also got a lot of press actually, and a lot of attention along these papers. This came out in July 2024, where they say that now they can give a polynomial time classical algorithm for noisy quantum circuits. Okay? When you get into this polynomial has an exponent of 1 over epsilon. Actually, this is, I copied out the theorem. They call it gamma there, but this is my epsilon, 1 over gamma. So they have an exponent 1 over epsilon, 1 over 2-qubit error rate. So let's check a normal error rate, 0.01. It's actually an error rate that we have now in devices. We have even lower ones. Okay, let's check out if we plug in, so X plays the role of let's say how many qubits you have, or the n times L, and one would get, if you would plug it into the exponential formula, which is roughly 1 plus epsilon times x, it's the same as e to the x time, epsilon times x. And then you would get like a number of 3. Here, with their method would give you actually, if epsilon would be 0.01, a polynomial method, where the polynomial method would have an exponent, which is 2 to the 650. I would never allow you to run a classical computation with a polynomial method. Don't never do that, which has an exponent of 2 to the 650. Don't even do which has a polynomial of 100, but this is like 2 to the 650. And read the paper, it's really that. Okay, so now I'm going to conclude. The myth was that quantum error mitigation cannot be useful due to the scalability limitations revealed by recent no-go theorems. And I would say 2 things. This was revealed much earlier, and admittedly, error mitigation techniques scale exponentially with the system size. However, due to the small prefactor epsilon in the exponent, you remember it was exponent of epsilon times n times L, one cannot rule out to have good circuit sizes that will be useful. And I'm going to analyze this in the next myth. Myth 2? Yes.
Sorry, Zoltan, can I ask?
Of course.
You listed those error mitigation methods, and the most favorable one in terms of this overhead was this tensor network error mitigation. So, but as the name suggests, when you have tensor network, then you have to, okay, you didn't explain what it is, but you have to contract some tensor network.
Exactly.
So,
and the contraction has also some classical overhead, which can be given depending on epsilon, and usually that scales less than this. So this is in time, this is the biggest one that you have to take this type of big number of samples. But in that paper, in the tensor error mitigation paper by Sergei Filippov, he actually has a full table, not only with the sample scaling, but how much it does cost to, also you have to ask how much does it cost to characterize the errors. Actually, there is another place, because in three of these, well, okay, it depends. In 2 of these, for sure, in the PEC and in a TEM, you have to characterize the errors. It is also a large cost. And you have to do some calculations also, which is basically have a heavy overhead only in TEM. Also a heavy overhead as a classical calculation. But I will talk about maybe now, or actually I will come back to this question how in the myth 2 when I compare to this. But that overhead can be also mitigated. Okay, so my verdict was that one cannot rule it out. So now myth 2. So okay, people who realize this, they say, okay, yes, you are right. Maybe it was overhyped that now we have this exponential scaling. Maybe it doesn't mean too much. In principle, but in practice, the circuit sizes that you can reach are not big enough to do anything. So myth 2 is solving practical problems require much larger circuits than feasible on quantum hardware without error correction capabilities, which means using error mitigation only.
Can I ask
Yes.
So in this theorem, in the end, you bound this difference between the ideal expectation value of observable from this simulated one, yes? And you bound it this difference, and you say that, okay, you need this much overhead to make it good.
Yeah, in this one, I would say yes, in this one. This is the most rigorous one with the PEC, I agree.
No, my question is, so here you state that this overhead is required if you want to have it satisfied for all observables? Because maybe there is also some way around that, okay, if you just focus on some observables, maybe for them you can do something better or not?
Absolutely, and this is the case. So basically, this is for all observables. Well, to be fair, it's for all Pauli string observables. It can be any, it can have any big Pauli weight, but it has to be a Pauli weight observable, not an arbitrary linear combination of them, one of them. So I have to be careful here, because both PEC and TEM right now is using errors that are tailored, and you can tailor it. It's so-called sparse Pauli-Lindblad errors, which means that the errors have a very special form, and you can get that error with doing this, which is called Pauli twirling, or sometimes it's called Pauli twirling. So, but yes, the answer to this is that if you have, you can have some observables and some situations where you don't need to remove all the error, that's just some errors, and you get a smaller overhead. That's also very true. Yeah. Okay, so myth 2. Okay, was that there? Okay, maybe you are right that exponential, exponential wall, this exponential wall, could be, it does not mean that there is no practical thing, but this exponential wall is going to be so close that we will not be able to do anything interesting. So let's have a look how close it will be. So I'm listing here a couple of recent results. IBM Eagle, IBM Heron. By the way, IBM Heron will give smaller errors. Now, Quera, IonQ Forte, Quantinum, and Oxford Ionic. So you get these 10 to the minus 3 till 10 to the minus 4 errors. And by the way, people believe that you can push down for sure trapped ions for sure to 10 to the minus 5. For superconducting qubits, 10 to the minus 4, they say for sure. 10 to the minus 5, some people say it's just a fantasy. Some people say it might be. So these are the relevant error levels. 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. Okay? Then, how should we calculate the, like, what type of circuits we do have? So we have this formula that the number of samples you have to take is e to the epsilon times n times L, okay? If you take e to the 10, that's something like, if I remember correctly, 26,000 something. So then, and if you remember, if you have ever played with the IBM quantum computer or a Rigetti one, you could like 10,000 or even 100,000, to be honest, even 1 million if you have good contact with IBM, is not a huge amount of samples. So 26,000 is okay. So then we should look into this equation that epsilon times n times L should be equal to 10. Okay? Let's use this. So then the circuit, I will go, the circuit sizes that you can feasibly run is 100 by 100 today. Actually, I had a paper out recently, this week. Of course, I was just a middle author with Algorithmiq, IBM, and Trinity College, where we run with the tensor network error mitigation method, a 91 times 91 big circuit, so 91 qubits, 91 depth, and we got out very precise expectation values. They were a dual unitary circuit, and also we went away from the dual unitary point of view. So it really works. And then you can, for the 10 to the minus 4 error level, which is maybe next year, run 300 times 300 big circuits, or maybe you are interested in more deep circuits by 100 qubits and 10,000 depth. And if you reach to the 10 to the minus 5 level, you will be able to run 1,000 by 1,000 circuit, or if you want to do really, really deep circuits, you can run 100 qubits and 10,000 depth. Sorry, you had a question.
Yeah, just to know, the thing you presented before was asymptotics, right, in big O notation. So here it seems you would like to infer from concrete numbers, the number of samples, but they can hide very large constants.
Okay, okay, look. So what I tell you, it's like in the theorems, in those very precise theorems, it depended on the noise type, let's say, what type of noise you use. And then they had this big O notation, and they didn't discuss the constant. But we know that's the sort of a lower or upper bound. It depends on the But these methods, the TEM and the probabilistic error cancellation has exactly, like if you have one type of noise, which is sparse Pauli Lindblad noise, it's not big O notation. It's exactly, even the coefficient is there. The coefficients are exponential to the epsilon times n times L. This is what you will have or 2 times epsilon times n times L if it's a PEC. This is what you will have for certain noise types.
But I guess only for a very specific error mitigation technique, because they
PEC.
Yes, because there can exist many, so maybe for others, we only know the big O. And
yeah, which means that you want to make it even better.
Okay.
I mean, if it's I mean, of course, okay, let me tell you something. For example, that's a very nice error mitigation method. It has its own issues because also some other noise thing comes in. But suppose your measurements would be perfect. There is a very nice purification-based method, which is of the following form. Basically, what you do is that you run 2 quantum circuits, 2 noisy ones, let's say with epsilon errors, and the same quantum circuits. And then sort of like do a swap test type of thing, and then only select on the good outcome, like when the outcome is when it succeeded for these n qubits. And then what you will have that your noise level decreased from epsilon to epsilon square, and you didn't have to know anything about the noise. And this is the overhead. Well, it's 2 times epsilon times L now. So there is not a specific noise thing. So they are different. Like it has a bigger overhead with these 2, but they are like different. And also now I'm saying that there are no measurement errors, which is far from true, like really far from true, because measurement has like 1% error, and they are good measurements then. But I mean, it's still like we are there. I mean, we really run those circuits 91 by 91. Monday, look at Monday archive. So I'm not, these are like not fantasies, I would say. We are here at this 100 times 100. And I mean, nobody's criticizing that. So if you remember, this is the next thing I'm going to talk about. There was this infamous, or famous, I would call it was a nice experiment, just IBM maybe pushed it a little bit too much. There was this experiment, the utility experiment, which was 127 qubits. It was shallower than our circuit, this 91, and also not on a line, but on something a little bit different graphs, okay? Nobody told, actually, the only criticism there was that actually you could classically simulate that. But actually when you classically simulated them, and the IBM people used the wrong method, they should have used some other type of simulation method, actually. And when the guys simulated it, exactly, because they could classically simulate it, they got exactly that curve. So I mean, these numbers are not numbers that, they are like really the ones that you will be able to run. And now the question comes, can you put in something interesting in those numbers? Interesting, for sure, but interesting and classically non-simulable. Okay, I mean, that's a sort of interesting question. Of course, I mean, we know that we can put in sampling type of ideas, but they are at the moment not.
So what kind of circuit is in your paper?
So it's a dense circuit which is modeling Floquet time evolution, which resembles like a tilted field Ising model, but also it has a dual unitary property sometimes, which is a special one, and we also went away from the non-dual unitary. And what we looked into was how the correlation function decays, with time correlation function decays, actually. So what I'm going to put here is some ideas about what could happen in the future if you accept that. Okay? So this is this type of what you asked, the great question. This is like the brickword circuit. So it's a kicked Ising model, another Floquet dynamics. So if you get to later on to the 300 by 300 regime, I mean, what you could do, again, is still only time evolutions, I would say, which could be interesting. You would not be able to do, let's say, a variational circuit, which is very interesting. But time evolutions, I mean, you can do always, if it's a continuous one time evolution, you can always do this trotterization. But that has a huge overhead. But instead, there is something called the variational Hamiltonian time evolution method, which I will talk about a little bit later, And maybe there you can run, typically what people want to run is Hubbard dynamics. And also in the 1000 by 1000, it would be good to do a Hubbard dynamics that would be not, where you could get out some information and it would be not classically simulable. Well, let's see what happens. But these will be, like, this is what we are saying, that if it's 1000 by 1000, you can maybe even get out some information which could be relevant. It's not like ground state, but some properties like dynamic information or something like that for relevant, useful systems.
Sorry,
yeah.
Do you think this could be a better approach than quantum simulators?
Very good question. I'm not saying that. Quantum simulators I also like. What happened with quantum simulators, from my point of view, I really like quantum simulators, but from my point of view, what happened there was that the bosonic quantum simulators, they work perfectly, but then also the classical simulation of them were somehow not so hard. For the fermionic ones, it would be super hard. I mean, I was in a project when I started my first postdoc in Torino, which was about these simulations. We went to, Immanuel Bloch was also there, we went there, and this was, I'm very old, so it was a really long time ago, to Munich, and in 2010, and he said, yes, I'm gonna try and do the Fermi-Hubbard model in a 2D Fermi-Hubbard lattice of Fermi, and then I'm going to run and get out some dynamical information. But now it's 2024, and now, okay, I hope for them. I would love that. It would be a beautiful quantum simulation experiment, like you mean the continuous time quantum simulation, but this is yeah, that's a good competitor to this, by the way. But let me just give the verdict, or our verdict, because this reflects, we want to come out as a paper with this. This reflects the idea of many people. So I would say that those finite circuit sizes that we showed, like the 100 times 100 to 1000 times 1000. By the way, just to get into your critical mode, because I felt a little bit critical towards early fault tolerance, let me tell you the bad news before I tell you the verdict. I don't think anybody can realistically expect a quantum computer circuit which is not fault tolerant that would run circuit sizes which is beyond 1000 times 1000. I mean beyond, I don't mean 2000 times 1000, but let's say 10,000 by 10,000. No way. Nobody would believe in 10,000 by 10,000 now. Nobody. So this 1000 by 1000, I would say, and around that, that's going to be a hard limit. And the hard limit is there. So for the critics, this could be the good news if you want to criticize near-term quantum computing. You can only run up to 1000 times 1000. And that's actually a hard limitation, to be honest. And this is what I'm saying, that actually those finite circuit sizes are still huge, and it's to be explored. These what one can run 100 times 100 to 1000 times 1000. And however, it's questionable whether practical quantum advantage, or not questionable, it remains to be demonstrated whether you can get practical quantum advantage there. If by practical quantum advantage, now this comes a subjective view, you mean something which for physicists is semi-interesting, let's say some Fouquet model, but an interesting, not like a very contrived Fouquet model. A Kick-Ising model is not a contrived model. Physicists worked on that before quantum computation. Not a contrived, let's say, Fouquet time evolution, and you can get out some physical information that you cannot get out classically. If you call that practical quantum advantage, I would maybe yes. Then my view is that in 5 years you will be there. I think you will get such an experiment. This is my particular. Of course, I have no proof of this, but this is my view. So I would say that practical quantum advantage remains to be demonstrated. Okay?
But then we are also in the regime where basically we are at fault tolerance limit, yes? Because this 10,000 times 10,000 will be like epsilon 10 to minus 5.
Exactly.
Exactly, quantum error correction.
I really like your question. I really, really like your question. And I'm going to answer it now. And I'm going to come back exactly to the question. Myth 3. Quantum error mitigation and quantum error correction are two different words. As we pass a break-even point, error correction will make error mitigation obsolete. Let's talk about this myth, and I'm then going to address your question very precisely. Okay, so let's just make 4 simple points on this. So, well, the threshold theorem suggests that once you are beyond break-even point, increasing the size of an error-correcting code leads to an exponentially lower logical error rate. So you would think that you are at the break-even point. We just reached it, a couple of companies, actually amazing experiments. Now we are entering the era of fault tolerance. However, I would claim that reducing physical error rates will likely progress slowly, and scaling up devices while keeping error rates low will experimentally be challenging. Meaning that maybe you can do 1000 by 1000. This is what IBM originally wanted to do. Maybe they still want to do. So do one very good logical qubit on a surface code of 1000 by 1000. Also, Google had this on their map. Okay, probably they will be able to do it. I don't know when. Maybe it could be several years, because now what they demonstrated is that there is this exponential lowering of the logical error rate, but I mean there are many questions still to be asked, and these were much smaller codes. But then, if you want to match up those numbers, like 1000 by 1000 or 100 by 100, then you need 100,000 or 1 million qubit, and this is what they want to reach. If you look at those early meaning COVID, pre-COVID type of, there were these very nice white papers with these progression tables, how they will progress. In all of those companies, they went into 1 million qubits. And the 1 million qubits was supposed to be in 2029 for Google. Then it disappeared at 2029, but okay. And for IBM, they didn't dare to write a number there, and so on, okay? Of course, there are other companies like PsiQuantum who are saying it's going to be in 2026, but okay. I'm happy to bet if somebody wants to bet with me. Okay, so the answer to your question, yes, we would be at that regime where you could do 1 qubit. But then if you want to do with 100,000 qubit, can you still keep that low error rate? Can you still do all the cooling down and everything? And I would say after a while you can, but this after a while is a question whether it's in 10 years, 20 years, 30 years. Am I still in academia in 30 years? I don't know. So that's the nicer question to ask. That is even a worse question. Okay, okay. So what I would say that there is this early fault-tolerant quantum computing regime that we are slowly entering. Quantum physicists tend to like this abbreviation like NISQ, so they call it EFTQC. It's not that nice as NISQ, EFTQC, but EFTQC, okay? Where we have limited physical qubits and near threshold error rates or before, and then we have to balance between logical gates, like how many of the physical gates we use to build up a logical qubit, and how many of the and then the precision, and then how many logical qubits we want to have. And okay, because of this balancing, you will never have like really good errors. I mean, original, like probably you can go down. This is what people call this EFTQC era, when you go down from 10 to the, so you have like 10 to the minus 4 errors, let's say, and not correlated. And then you do logical qubits that have 10 to the minus 6 to 10 to the minus 8 errors. This is what they call this era. And but then you also have to, you run into these same issues that if you have a deep enough circuit, even with 10 to the minus 6, you have issues with working with those logical qubits. And what you have to do is error mitigation. So those things that we are developing now for near-term computers, they will be also very useful, or they will be actually a key part in the early fault-tolerant quantum era, which will hopefully come in our academic lifetime. I'm really hopeful of that. And this means that quantum error mitigation methods designed for physical errors can be adapted to logical errors. Of course, there are specific challenges here. I mean, first of all, you remember the same formulas will be true. So e to the epsilon n times L, that will be true always, again. However, there will be specific challenges. One challenge is that, how did I calculate this e to the epsilon n times L? Well, I said that e to the 10 is equal to, or how did I calculate effective circuit sizes? I said that e to the 10 is equal to 26,000, and e to the epsilon times n times L is equal to a to the 10, and then epsilon n times L is equal to 10. This is how I did these calculations. The problem is that for fault-tolerant quantum computers, these times, like the gate times and the circuit times, will be much slower. So then it's questionable whether that 10 is okay, like 26,000 is really, to that take, well, maybe it's a good formula to use, but that's a problem. There is also a problem that the errors are smaller. So if you use a method where you want to characterize the errors, you will have to have more pre-processing characterizing the errors. There are still some good things there, though. One good thing is that The errors are, of course, sometimes of specific form. And secondly, that the errors are often known how the errors behave, and you can adapt it to this. So it's still hopeful that you can get out of these early fault-tolerant machines something using error mitigation, but you have to use that. So I would say that we debunked this. So quantum error mitigation and quantum error corrections are not two different words. And as we pass the break-even point, error correction will make error mitigation obsolete. This is not true, because instead, different generations of quantum hardware will likely undergo continuous evolution, and quantum error mitigation will be a major enabler in all evolutionary stages until full fault tolerance is reached. Okay? Let me say one important thing here, which relates to your question again. Suppose now that we have the fantastic thing which would enable to run in early fault-tolerant era, like we have 100 physical qubits consisting of one logical qubit, let's say, and we have 100 of those logical qubits, or 1,000, 100. And then we run a circuit that is 1,000 deep depth, okay? And maybe we can do it even without, let's say, error mitigation. So aren't we in the same problem here, that we are still competing with classical methods, and we have all these issues, and then we still have to build up larger and larger circuit size. And here I'm bullish on error correction, good fault-tolerant error correction, because if you can run some circuits with error correction and, let's say, sample from it, so without using like really hard error mitigation methods, then there will be one different thing that you can do compared to the current error mitigation methods. Namely, you can sample from the states, meaning that you are not correcting on expectation, not correcting the expectation values at that time, but correcting the state. And you have really that state there, not an expectation value, but really you have that state. And that would enable you something that classical computers cannot do now, because the best classical methods, how did they beat the Kick-Tizing model IBM experiment, this utility experiment? Well, they beat it because they were looking at expectation values, and they could actually use this type of backward Hamiltonian dynamics to calculate those expectation values. But such a numerical method would never be able to sample. And then comes those important things where you are able to sample. If you are able to sample, you can do two things which are important. One is generative quantum machine learning, so I'm bullish on that. So sampling from probability distributions that you cannot calculate, you cannot sample, you make a classical algorithm that you cannot sample from them easily. That's I'm bullish on. And secondly, then you are also able to do measurements of very complicated Hamiltonians through phase estimation, because for phase estimation, it's not that the final state you want to know the expectation value with some trickery, but you want to have the final state there and then do the phase estimation. And phase estimation you will only be able to do then. Okay, so let me go back to one more myth, which is important. How much time do I have?
Like 10, maybe minutes.
Okay.
Yeah.
Okay, sorry for taking this long, but so the myth 4 was that, which you can hear a lot about, is that in the NISQ era there were a lot of variational quantum algorithms that were developed because they couldn't run those orthodox quantum algorithms. So myth 4 was that variational quantum algorithms require exponential training due to Barren plateaus, and thus cannot be useful. This is this famous Barren plateau problem but Let's think a little bit around these points. So first of all, it would be, of course, very hard to accept that we cannot use variational quantum algorithms. Why would it be hard? It's not because they are NISQ-tailored, because if you think about your life, your current life, in your current life, you are using Google, you are using ChatGPT, and it will become more and more. All these are based on variational methods. Like all these are based on neural networks, variational methods, classical variational methods. So I mean, if you want to throw away that type of word in the quantum regime, then that's maybe not so good. So these like classical method, classical word, it's extremely effective to solve different type of problems to use variational methods. So I mean, it's very, very natural to explore them in the quantum regime, like whether this can be combined with some quantum speed-up algorithm. Okay, and related to this, of course, that variational quantum algorithms, they have a lot of flexibility and adaptability towards near-term hardware. Okay, that was the reason they were bringing these up in this NISQ era. But I mean, I will talk about the final myth, which is around this, that maybe not in the NISQ era. We can also do something maybe in the Voltron era. But there are these trainability issues and Barren plateaus. What is Barren plateau? Like roughly speaking, it means that the loss landscape becomes flat. So how flat? Okay? And in which way flat? These are the two important questions. So in the which way, how they prove it, is that they take a particular type of variation algorithm with a lot of parameters, and then they randomly select parameters. Okay? And for example, this was done for certain variational quantum eigensolver variational quantum eigensolver systems, like circuits, parametric circuits, and here you can see the number. So if you look at the probability of having a gradient greater than 10 to the minus 3, currently, if you are measuring very, very, very precisely, but you have to be really careful, then maybe you can measure a gradient 10 to the minus 3. We have also a paper out last week where not gradients, but we measured some properties with 10 to the minus 3 precision, but you have to really be good. So greater. If you have a circuit which with depth, qubit number 50 and depth 500, then they become really small, this probability. Actually, if you have more qubits but shallower depth, let's say 100, and then the depth is 50, then it's actually a little bit better, 10 to the minus 9. But here these numbers are extremely small still, so it seems that, okay, it's over for variational circuits. But is it over? Of course, there are some catches here, because what did I say? What I said was that this is for random selection of parameters. But it's not always that you have random selection of parameters. For example, even in this, in the standard, let's say, unitary coupled cluster ansatz, actually, using just some classical calculation, the classical coupled cluster ansatz, you can put in already those good parameters that are relatable to the classical normal coupled clusters ansatz and start from them and tweak them only a little bit. And this is the same thing with this Hamiltonian time evolution variational ansatz that I talked about, that you actually from a trotterization, you know roughly what those parameters are, and you want to tweak them only a little bit. So for so if you would have a domain-specific knowledge like that, then there could be an effective training, maybe at modest certain sizes, but modest could be like 100, 200, 300. But this lies out of those formal analysis that is done for the Barren plateaus. Okay, there is also another way out, namely that there are some certain variational circuits where you could actually you can prove that you don't get into a Barren plateau, but then for all of these until now, you could see that you can classically actually do with classical methods, you could classically simulate the variational adjustments or the optimization, but just the optimization. Actually, there are circuits that are very nice. For example, circuits in generative quantum machine learning, where actually you can classically optimize pre-trained a circuit, but you would not be able to get those samples. Again, the sampling comes in. So, so basically, I would just go to the verdict that that while training unstructured quantum circuits at scale looks unlikely, the prospects of some problem-inspired models equipped with special initializations remain undetermined. Maybe one could do something. And another one could be what I mentioned, that the quantum computer might be necessary as an initial data collection phase or as a sampler, and or to be required to sample solutions where we can do the variational training classically. This could actually provide opportunities for near-term quantum advantage. Even in the cases when the training process is dequantized, because what the people did was that the training process was dequantized. And just to finish, I don't know if there are any questions around this, I will go to the fifth myth, because this was about variational circuits and mostly like in NISQ. But people are also believing that this variational world is only the NISQ world. But this is also a myth. By the way, just to tell you that here, we didn't debunk this question. We put it in an open one, so we don't know whether this will survive. But what I can tell you is that if it survives, then variational circuits might not only be important in the NISQ era, because that's the myth 5, quantum error mitigation and quantum error corrections. Oh, sorry, this is not the one, but I don't know how it went. So the fifth myth is this one. Let me, variational quantum algorithms are only relevant in the NISQ era. This is my myth 5. And I would say that partially the reason for this was because they thought that you would have to have very precise angles when you do these variational algorithms. And actually it turns out that you will have to. You should have those precise angles. And for the precise angles, people thought that you have to have a very high T-gate count. You know, in photon and quantum computation, what you have are the Clifford gates, which are easy to make in principle, and then there are the T-gates, which needs like T factories of sort of noisy T-states, and then you do, based on Clifford gates and Clifford operations, distillation to a not noisy T-state, and from then a good distillation of gate, operational distillation to a T1. And that's a hard thing. But it turns out that actually those same methods that are used in error mitigation, with those same methods, you could do actually, you could use only, like what you can do is, for example, that if your angles are pi over 16, like you have pi over 16, 2 pi over 16, 3 pi over 16, and so on, it turns out that actually you can combine circuits with angles like that, with plus minus signs, again, very similar to the probabilistic error cancellation, in a way that actually the expectation value at the end gives you the correct expectation value with the angle that is of precision 1 over 16 squared. So this is what I want to emphasize, and it's going to be has to be used in quantum error, in photon and quantum computing, because, for example, if you want to do, let's say, a quantum phase estimation, you still want to produce a state which is pretty close to the ground state. How can you produce it? Well, there are different type of ideas, using adiabatic ansatz, using Gibbs sampling to very low temperature. But one way would be to do some variational stuff. So this is the fifth myth that I wanted to discuss, and And let me read our verdict. While some technical challenges such as high circuit repetition and finite rotation angle resolution need more attention, the community is making rapid progress in addressing these, and variation algorithms will have useful applications also in fault tolerance. This is what we believe. And I emphasize again why this is important, because after all, classical computing is an extremely mature technology, and variational methods are very prominent in that field. So it would be weird if it would not be prominent in the classical world. So thank you very much. With this, I would like to close.
Thank you, Zoltan, for a nice talk. Yeah, we have, I guess, some time for questions or comments to the speaker. Marco?
Yeah, thank you. I have a general question regarding this no-go with the scaling with error mitigation.
Yes.
So I would like to understand better the type of noise for which they apply, because I can give example of noise in which you apply, for instance, take a state that is plus, you just apply polybit flip, it will be insensitive to the noise. That's a stupid example, but just to say that not all noise makes you converge toward the identity. So are there, I mean,
yes,
there are some hardware platform which can have a specific noise model and that are not, that will not make you converge toward the identity. So are there no-go for these kind of things? Or?
Yeah, so for sure, okay, I have a very positive news here, that it is known that there are types of noise which are, because for unital noise, okay, let me start with unital noise. However low level the noise is, in the end, you will converge to the identity.
But here, even I'm not.
But let me tell you, but if you don't have unital noise, there is actually a very beautiful paper by Gottesman that one can show that for certain non-unital noise models, you can actually do, if the error rate is low enough, universal quantum computation. It's not known where the threshold there is. There is a similar, like in error correction threshold theorem, where the noise actually, basically what it does is that it brings some of the qubits back to the zero, like to a pure ancilla state, and with clever tricks, he showed that actually one can do universal quantum computation, which means that actually it's not true those theorems for arbitrary noise. So there are noise where these theorems do not hold. That's known.
Because my point was that even for unital noise, I will take again the example I said. Imagine, I guess it's maybe on average initial state or something like this, because if I prepare the state plus, and I apply a noise that is, you flip a coin with probability 1/2, you apply poly X, otherwise you do nothing, the state will be completely insensitive.
So let me give you another example where the state is not insensitive, and then I will clarify the conditions that they are using. It will be more or less clear. You can also think that N is very big, but the depth is only 1. And then you do, let's say, your noise level is, let's say, 0.1, and it's a unital noise. And what happens is that each of the, and it converges to the identity. Like let's say that you do the noise is that with 0.1 you put identity. Okay, so then one can say, but Zoltan, where is your exponential overhead? How you can resolve the identity state and this state? Because here. 90% of the qubits will be in state 0 still, and only 10% will be after layer 1 in the identity state. I can easily resolve. Yes, because I didn't tell you about those small nitty-gritty details when this is true. And those no-go theorems are true. For example, if the circuit scrambles, this is definitely not a scrambling circuit. Or if it has a certain structure and at least logarithmic depth, this type of.
Sometimes worst case. Those are worst case results. Sometimes, I guess.
Worst case in the sense of.
That you optimize over states.
That's big.
Yeah. Then, for example, this ICERT result, they have a depth of log, but then they optimize over. Then they are averaging over all initial state, like 0, 1, 0, 1, 0, 1, and stuff like that. So there is always these small details. So it's true, not for all noises, not for all, even if the noise is not very special, but the circuit structure is special, then it's not true anymore. So these are, yeah.
Okay, thank you.
And also the worst case, what Mio said, yeah.
Any other questions or comments? Just me, I have one question, because you were sort of quite optimistic regarding the absence of barren plateaus.
Optimistic or pessimistic?
Well, optimistic about that for relevant cases there will be kind of absent, right?
Yeah, and you remember, I was like, this was the only one where we put not to the debunked, but the open, yes.
Okay.
Partially optimistic,
okay,
yes.
But like you mentioned, you referenced classical. That like when you have classical ML,
yes. Yes.
Like algorithms, you don't see, or maybe the algorithms somehow circumvent this problem in practice. So are you? But like I
very good question. Yes, I have an answer.
But are you aware of? Because I'm not like about results about barren plateaus in the classical problems. Are there some concentration of measure results that guarantee that gradients vanish or not in the generic case?
So in the generic case, they vanish there as well. So they have this barren plateau problem. There is one big thing why in the practice they still work. Actually, because calculating gradients up to very high precisions classically is much easier than measuring gradients with a quantum computer up to very high precision. So 10 to the minus 3 would be nothing for a classical computer. For us, this is like the limit. That's a very pertinent question, actually, Michał. Thanks for that, because this is actually something I should have mentioned, because that's why barren plateau is kicking so hard. Yeah.
Okay. Yeah. If there are no more questions, let's thank the speaker again.
Thank you.